All right, so we're at class 28. You only have one more homework assignment. It's due on Thursday, the 6th of December. A week from today is when that second Chapter 7 assignment is due. Today what we're going to do is cover some more information having to do with energy loss, both due to pipe friction and also local losses. And then we're going to go into grade lines, which is a way of kind of illustrating energy losses in a graphical way. Any questions before we move on? Okay. Well, we've talked about how energy is lost partly as a function of how rough the pipe is. You know, water's flowing through a conduit, and at the edge of the flow boundary, where the water is in contact with the surface of the material, it's going to experience more friction if you have a really rough surface, let's say a rough concrete surface compared to a smooth glass surface. This table is provided. It's information that relates the roughness of pipe in terms of an equivalent sand diameter. The idea here being that if you were, each of these may have irregularities in the surface, but if you were going to represent how rough that surface is in terms of if you were taking spheres, what would be the diameter of those spherical grains. And so in the case of cast iron, which is a pretty widespread pipe material, you'll see that new cast iron has an equivalent sand roughness of 0.26 millimeters, or in terms of feet, 0.00085 feet for cast iron. You can see that there's some pretty weird pipe materials there. Wood is on the list of pipe materials, and in fact it was common long ago to make water distribution pipes made out of wood in the same way that barrels were used to transport liquids. So wood was used for pipes as well. This just illustrates that different pipes have different roughnesses, and even when you're using the Darcy-Weisbach equation, which is this more sophisticated way of accounting for friction loss compared to the Hazen-Williams, in the Hazen-Williams equation, that C value is supposed to be independent of flow conditions, and it's only applying for water at a certain temperature and over a very narrow range of flow velocities and pipe diameters. So the Hazen-Williams equation has some built-in inaccuracies because the C values don't respond to changing flow conditions. This Darcy-Weisbach equation is a little bit more powerful and more accurate because the friction factor F does take changing flow conditions into account. You start off by asking yourself, what is the pipe material? And so, for instance, if we had a galvanized iron pipe, which has an equivalent roughness of 0.15 millimeters, the way that you use this Moody diagram to get the friction factor F, you'll notice that on the left side of this vertical axis it says friction factor. You start by calculating the relative roughness. So the relative roughness is the K sub S, which is the same thing as epsilon on this table. So some texts use the equivalent sand roughness variable epsilon. Sometimes it's K sub S, but it means like the equivalent sand diameter relative to the diameter of the pipe. And so, for instance, if we have a pipe diameter and it's made out of something, so let's say that we have here cast iron that we're using, then we would go to the table and we'd say cast iron that's new has a equivalent sand roughness of 0.26 millimeters. So epsilon is 0.26 millimeters. Well, if this pipe diameter is 500 millimeters, then what we'd need to calculate is the ratio of that equivalent roughness to the diameter of the pipe. So 0.26 millimeters divided by 500 millimeters. Okay, so I don't happen to have that calculated. Let's find out what is the ratio of those two. And then we're going to use it to start off with the right side vertical axis. So 0.26 divided by 500. Okay, so it's 0.00052. 0.00052. And there's no units there. It's a unitless ratio. So the relative roughness, you'd find what's close to our number, 0.00052. So here you can see it's nonlinear, by the way, but we'd find 0.004, 0.0006. So we're going to be kind of in between those two. And then we would follow this curve over until we intersected the Reynolds number for the flow conditions in that pipe. So you would have to know, for instance, what is the velocity through the pipe, because Reynolds number is the velocity times the diameter divided by the kinematic viscosity. So the Reynolds number is going to depend on the viscosity of the fluid. And remember that the viscosity of the fluid is dependent on the temperature and what the fluid is. And so water is going to have one viscosity at room temperature and a different viscosity at 50 degrees Celsius. And likewise, the viscosity of oil is going to be different than the viscosity of water. So the power of this Darcy-Weisbach equation is in part related to the fact that the Reynolds number you're calculating is very specific to the actual flow conditions that are in that pipe. So you'd have to find your Reynolds number based on what is the fluid, what's the diameter of the pipe, and what's the velocity that water is going through the pipe. And so we're in between these two lines, and you'd go up until you intersected with whatever your viscosity is. Now here on the horizontal axis, note that it's logarithmic. And so if we had, for instance, 1.5 times 10 to the fifth as our Reynolds number, then here'd be 1 times 10 to the fifth. Here's 1.5 times 10 to the fifth. So we'd go upward until we intersected that curve that we're following in between the bounds of the 0.004 and 0.006. And then we go over to the left to find out the friction factor F. And so it looks like it would be maybe around 0.0195. So this Moody diagram is just one approach for calculating the friction factor. It's probably the easiest way is graphically. Next semester in hydraulic engineering, you're going to learn two other approaches. One is called the Colebrook equation, which is an implicit equation that's very accurate over a wide range of conditions, and so you can calculate the F value. Instead of having to use a figure, you can use it with an equation. And then another approach is called the Jane method, and it's not an implicit equation. An implicit equation is one where the unknown is on both sides of the equation, so you have to solve it iteratively. The Jane equation you can calculate directly, and so it's easier to solve, but it's just kind of an approximation that can have error at some of the extreme flow conditions. But I just wanted to show you a little more information on if you're going to use this Darcy-Weisbach equation, you have to know the friction factor. But sometimes the trick with that is that you don't know what the velocity is when you start solving the Darcy-Weisbach equation. And so just using this can be iterative because you have to know the velocity to find the Reynolds number, and you have to know the Reynolds number to get the F value, but then the flow velocity depends on the F value. So there's a series of techniques that you'll learn next semester for how to solve this iteratively, starting with the guess value for F and then checking the guess and making a correction and so on. For now, just be content that there is this thing called a Moody diagram, and that's where you get the F value for the Darcy-Weisbach equation. Any questions so far? All right. Yesterday in lab, you took some pressure change measurements to try and characterize local losses. And sometimes local losses are called minor losses. But that's a pejorative term that makes them sound like they're unimportant when really they are important. So we'll call them local losses instead of minor losses. Like I mentioned in the lab yesterday, the cause of this localized reduction in energy is the fact that when water is changing direction, there's a separation zone where there's turbulence inside the fitting. And that turbulence is kind of like an internal location where the flow diameter, the effective flow diameter, is decreasing. If you have like an eddy where a certain section of the pipe, the water is going the opposite direction, then that means that the actual effective flow area has a smaller diameter. And so you're forcing the flow through a smaller effective flow diameter, then that's going to reduce some energy. It's as though the pipe is smaller for a certain section. The K value can be measured if you have a constant velocity both upstream and downstream as the change in head divided by the velocity head. And so you can add up all of the K values in a pipe system and multiply by the velocity head. As long as the diameter of the pipe is the same and therefore the velocity is the same, then you can calculate the minor losses by just aggregating the K values together. And we've already looked at the table of different K values, and so hopefully you remember how to apply those. We'll work an example in class on Tuesday next week having to do with a system that has lots of different local losses. We had one of the fittings that you tested yesterday, actually I think maybe the last one, was where there was an expanding pipe. And so in that expanding pipe, the head loss sometimes is calculated just in a simplistic way as the change in velocity squared divided by 2g. If you don't have a calibrated K factor and you don't want to apply that, because this is kind of like a quick and dirty approximation for the amount of head loss that's going to occur when you've got a changing diameter result in a change in velocity. You just say that it's the changing velocity head is how much energy that's lost. And if you have it discharging into a reservoir, then that's assuming that you're losing all of the velocity head because upstream the water has velocity and therefore velocity head, and downstream you lose all of that energy when the water discharges into a tank. Okay, so it's customary to draw sometimes sketches of where the energy grade line is and the hydraulic grade line, especially in the construction of water treatment plants. One of the big expenses of water treatment is the electricity required to move water from place to place. And so as much as possible, when they're designing a water treatment plant, they try to make it so that the water can flow by gravity. And in fact, there are some water treatment plants in the West where the water is coming from an elevated mountain reservoir, and they actually don't have to have any pumps in the system because they just have designed the layout of the system so that everything's downhill and there's enough energy because of that downhill motion that they don't have to move the water by pump. But when they create plans, they'll sketch out how much energy is in the water and what's the elevation of the water as they move through the treatment plant, so you can kind of see how much pressure there is. And that's what this is representing. The EGL, energy grade line, as it's abbreviated, EGL, it is, if we look at the three terms of the energy equation that address where the energy is, like what form, the EGL, when you graph it, is going to be the pressure head, the elevation head, and the velocity head. All three of the terms. The first two terms are potential energy. The third term is kinetic energy. So the energy grade line has all three. The hydraulic grade line, HGL, is just the first two terms. It's just the pressure head and the elevation head. It excludes the velocity head. So now if we look at this sketch, what it's saying is that inside of a tank, the energy grade line and the hydraulic grade line are just at the water surface in the tank. And so now think about what that means in terms of we've got some datum down here that we're measuring all of our elevations above. Inside the tank, we're assuming that water has no velocity, and up here at the surface, the water has no pressure. So in the tank, at the top of the tank, in what form is the energy at that surface location? Well, it's not in the form of pressure. It's not in the form of velocity. So all of the energy exists as Z. And so the energy grade line and the hydraulic grade line both have Z. And so the EGL and the HGL is at the water surface inside the tank. But then what about down below, like at a depth? How much energy is there at some point inside the tank? You know, are things different there where this is our datum? Well, we have less Z than when we were referring up to the water surface, but now there's pressure at that location. And so the pressure divided by gamma is going to, when you add it on, you'll have the same amount of energy anywhere in the tank as you did at the surface. But when the water starts to enter this pipe, energy is changing a little bit. Because as the water approaches that pipe, it's speeding up. It's getting velocity, whereas in most of the tank, the water has no velocity. In the immediate vicinity of the pipe, the water is accelerating in towards that pipe. And so if you're gaining some velocity, then that means the energy has to come from somewhere. And it's a localized reduction in pressure. And so there's a reduction in the HGL. Like the HGL is diverging. It's below the EGL. And the difference between the two is the magnitude of the velocity head. So you can see it saying V squared divided by 2G. So we've got two locations, location 1, location 2, and they're saying that the distance between the EGL and the HGL, like the gap between them if we graph them, is just the velocity head, how much energy there is. Okay, now you'll notice that both of these lines are angling downward. That means that the amount of energy is decreasing as the water flows through the pipe. And why do you suppose the energy is decreasing as the water flows through the pipe? It's pipe friction, that's right. And so the slope of this line, the slope of the EGL and the slope of the HGL, is dependent on friction losses. And so you can see here this H sub L, the head loss, is the distance between the original EGL and HGL, and then how much energy there is at any particular point. And so, you know, where is the energy at location 2? Some of the energy is in the velocity head, a small fraction of it. Some of the energy is in the pressure head, and then some of the energy is in the elevation head, if we're using this horizontal datum as our basis for measuring the energy. Now what about the piezometer and then this other device that's to the next, that's to the side of the piezometer? Well, the piezometer itself, the water level is going to rise to the elevation of the HGL. In fact, that's the definition of the HGL. Like if you put in some sort of a tube, the water level is going to rise because the pipe is pressurized. You know, however high the water rises to, that piezometric height is the hydraulic grade line. But the tube that's to the right of that piezometer, you can see the water level is a little bit higher. And in fact, even though it's further to the right, the water level is a little bit higher. And that's because, as you might guess, when you, instead of just having the tube connected to the side of the pipe, this tube is facing the flow, and so there's flow that's intersecting the opening of that, and we have a streamline that's dead-ending, and so it's that velocity head is exchanging into additional pressure at the stagnation point. We've talked about this before when we were discussing pitot tubes. There's a stagnation point at that opening, and it's pushing the water a little bit higher. And so now, when you face the opening of the tube in the direction of the flow, then the water level is going to rise to the energy grade line rather than just up to the hydraulic grade line. So we can get a physical idea of either the HGL or the EGL depending on how we connect some sort of a monitoring tube into the pipe. Any questions so far? Yeah.
So if there wasn't any pipe friction, then the EGL would be constant?
That's right. Yep. If there was no pipe friction, then it would be a horizontal line. Why is it that the EGL is above the water surface when the water comes out of the end of the pipe? So this is kind of showing like you got a jet of water coming out. Why is the EGL above that jet of water?
Because you still don't have some amount of velocity.
Exactly right. So you still have velocity, so you're still going to have velocity head. And remember that the pressure and the elevation are at the water surface. When you have just an open container of water, like we had the tank here, the HGL is at the water surface because HGL is the pressure and the elevation. So the HGL is at a free surface of water, but now this water is moving, so the velocity head's going to account for the EGL being above it. Here's what a pipe does. A pump. When there's a pump, it immediately increases both the energy grade line and the hydraulic grade line. And so however much pump head is being added, it increases the amount of energy. A pump, remember there are three places that the energy can be. Energy can be an elevation, could be a velocity head, and pressure head. And in this physical system, the pump is adding pressure. Because it's adding pressure, the water is flowing at a higher velocity than it would have flown if that pump wasn't there. People sometimes get confused and think that pumps add energy by increasing the velocity of the water, and they don't. Pumps add pressure. That's how, well, some pumps lift the water. You know, a positive displacement pump like a screw pump, or sometimes people will have pumps coming out of like a cistern that's like every time a certain bucket of water tips over, like you see at Disneyland or Disney World, you know, like it's buckets on a rope and it's going it's constantly rotating. That's called a positive displacement pump. And in that case, those kinds of pumps are lifting the water physically. But most pumps that are used in homes and businesses and municipal applications, they're accelerating the flow and adding pressure because of that impeller. And so that's what's happening here. As you can see that the water that's coming into the pump, first of all, I'll point out there's a downward slope because of pipe friction. So even if we didn't have these arrows, these blue arrows that's showing us the water's going to the right, even if we didn't have that, we could still know what direction the water is flowing by the slope of the energy grade line and the hydraulic grade line. That slope direction tells you that the water's flowing to the right. The other features to be aware of here is the gap between them is dependent on the velocity. So if you have a relatively slow moving water, if the water is going slowly through the pipe, then these two lines would be closer together because the velocity head would be minor. But the faster the water is moving, the bigger the gap is between the EGL and the HGL. So the water is going through the pipe, and suddenly the pressure increases. And so there's a vertical line due to that pressure increase, and then the water continues going downhill. The EGL and the HGL are decreasing in the direction of flow. And since the diameter is roughly the same, I guess the sketch isn't to scale, but we're saying the diameter is the same, and so the slope will be the same. the slope of the energy grade line and the hydraulic grade line, and the gap between them remains constant, both upstream and downstream of the pump. So pumps add pressure, turbines extract pressure. They take out pressure and turn it into electricity. So here's a turbine. We've got some elevated reservoir, and the water's flowing through a penstock, and then the water encounters this turbine that is spinning because the water has to flow through it to get to the lower discharge, to the lower reservoir. And so if you look at the EGL and the HGL, they're decreasing according to the friction loss through the pipe, but then there's a sudden loss of pressure. And that represents the head that's given up to the turbine. Look at how the gap between the EGL and the HGL is getting smaller here as the pipe is gradually expanding. Do you see how they've got one gap right after the pump, but then as you get further away from the pump, the gap is decreasing because that diameter is getting larger. Then that means the velocity is slowing down, and therefore there's a smaller velocity head that separates the HGL and the EGL. Okay. So in a nozzle, the water's flowing to the right. We know that not just from the arrow, but because the slope is going downward to the right. The EGL and the HGL are separated by the velocity head, but then we have this nozzle, the diameter is decreasing. And so that causes the velocity to increase. And we know that Bernoulli's effect is that if the velocity increases, then the pressure is going to decrease. And so there's a divergence between the EGL and the HGL. The distance between them gets larger. And then you'll also notice that the slope of the EGL is getting steeper, because if you have faster velocity, then the rate of friction loss is going to increase as well. And then finally, when the water comes out of the nozzle, the HGL is at the water, and the EGL stays above it. Okay, so here this is a big pipe that transitions into a smaller pipe. So big pipe is slow velocity. Small pipe, because of the reduced cross-sectional area, for the same flow rate, the velocity will be higher. So if you have a higher velocity, then that means the slope of the EGL and the HGL is steeper, because there's more friction loss. And then the gap between them is larger. Let me point out this, because this shows it nicely. You see how when the water flows into the tank, it's got these little blue lines? It kind of brings to mind like some discharge turbulence as the water goes into the tank. Remember that when the water is flowing through the pipe, it has velocity head. You know, it has movement, it has motion. But then when the water gets into the tank, there's no more velocity head. So that represents a loss of energy. And this head loss at the outlet, where they've terminated the HGL at the water surface, and this is really important. You will have a question on the final exam where you have to do a sketch like this. So you need to be able to draw them. We're going to practice that a little bit later. But at the tank, the HGL finishes at the water surface, and the EGL is above it. So the energy grade line kind of just goes from above it, and then suddenly it goes down to the tank level. And so that elevation represents the losses associated with the velocity head. And that's why we say K equals 1 for a tank, because you're losing all of the velocity head. 1.0 of v squared divided by 2g, when the water goes from inside the pipe when it had velocity, and now on the other side of the pipe, it no longer has velocity. So all of that velocity head is lost.
So, I got a question. Well, let's go into the tank, never mind. I'm thinking yesterday
Mm-hmm.
So you're losing velocity, but it's not going to be zero because you're still in a pipe.
Yeah. Yeah, so there's a velocity change there, but you're not losing all of the velocity head. Yep. This illustration makes the point that the EGL and the HGL is not affected by the physical elevation of the pipe. Like, these graphs are just a graph of energy. It's not a graph of where the water is. It's not a graph of where the pipe is. It's a graph of how much energy you have above a certain datum. And so you'll notice that even though the water in the pipe is going uphill and then is going downhill, that doesn't change the location of the EGL and the HGL. I mean, the conditions in the pipe are changing. For instance, as the water is going up, then you're gaining Z, but you're losing pressure. But the sum of those two things together is constant as you move up and down, either through the tank or in the pipe. Because remember, HGL is the sum of pressure head and elevation head. So when the water is going up in elevation, the HGL is unaffected by that change of elevation because you're simply exchanging elevation head and pressure head. Both of them still continue to slope downward at the same rate, the EGL and the HGL at the same rate, but it's any time the physical height of the water is above the HGL, then what that means is that you have negative pressure head. So that if we punctured the pipe, if we drilled a hole into the pipe, if the pipe is above the HGL, you puncture it, it's going to suck air in. Rather than water spraying out, you have negative pressure anytime the physical water is above the HGL. And so the pipe ends and you're back into a positive pressure section, but this has the potential for there to be cavitation. If you have too much negative pressure, then the cavitation could occur.
The same thing as back pressure?
No, I don't think so. This is sometimes called an inverted siphon, but suction and back pressure are different. You know.
Is that what you consider like when you go out to eat and you get a hole in your straw?
Yeah.
And you get the air in it?
It would, let's say you have a mouthful of soda and the straw is still in your mouth and you punctured it, then air would go in. Right? But if you just get a hole in your straw, then it's not full of liquid to begin with, you know? Yeah. So if you're going to draw one of these, the key features that you need to include in your drawing are, number one, that the EGL and the HGL are both at the free surface of water, that they diverge from each other when the water begins to accelerate to enter the pipe. So this little section where you've got a line going down, that is where you have convective acceleration. In a section of convective acceleration, the water is speeding up, and so it's losing pressure as the velocity increases. And then there needs to be a slope of the line, and like how steep to make it? Well, think about it. If you made it really steep, then what you're saying is you'd intersect the HGL with the pipe before the pipe ended. And what we know is that the HGL has to end at the free surface of water, and the EGL should be a little bit above the water when it goes to a free surface. And so sometimes drawing the sketch is kind of iterative because you won't know exactly how steep to make the line at first. And you'll see that on the handout I'm going to give you in just a moment. Remember that in a pump, it's a vertical line that's going upward. It shouldn't be at an angle. It should just be vertical, because what it means is that there's an instantaneous increase in pressure, that the pressure was decreasing due to pipe friction, but suddenly the pressure went up. Like as water is flowing through a pipe, it's losing energy. You know that. You know why it's losing energy, because of pipe friction. As water goes through this pipe, it's not losing elevation, right? It's a horizontal pipe. So it's not losing energy in the form of Z, and it's not losing energy in the form of velocity. It's not like as the water moves from left to right, it's slowing down, because if it was slowing down, continuity wouldn't apply. You know, Q in and Q out have to be equal. You can't have water slowing down in a pipe because then it would be piling up. And so you have to have the same velocity everywhere in the pipe. And so the only way that the pressure, that the energy can be decreasing is in the form of pressure. So pressure is decreasing gradually as you flow through the pipe, but then it suddenly increases due to the pump. Okay, so I have a handout for you. There's two sides to the handout. Feel free to collaborate with your classmates as you sketch these. Unfortunately, if you've printed the notes, you might already have seen the solution. So don't look at the solution. Try and do it from memory. Forget what you've seen if you've seen the notes. I would suggest doing these with pencil rather than pen. And it may be useful to use some sort of a straight edge, like a credit card or a ruler, something that allows you to draw a straight line. I certainly can't freehand a straight line. So draw the EGL and the HGL and follow the same kind of approach that you've seen in these following images. So slow-moving water versus fast-moving water. All right. So the water is flowing to the right. That means that the EGL and the HGL should be sloped downward in that direction. You need to label which one is which to make it clear that you know it's the EGL above the HGL. So why is it that I have this be relatively steep compared to the second pipe? The slope isn't as steep. It's not just because of that. I mean, it is related to the fact that one of the pipes is different from the other. Okay, good. Yeah, so he's saying larger pipe diameter in that second section, which means the velocity is going to decrease, and the slope of the line is related to the velocity. So if you've got a faster moving velocity, like we did in the first section, then it should be steeper. The slope of the EGL and the slope of the HGL will be steeper than in the second section. And that's also related to the fact that the gap distance between the two is less in the second segment. In the first segment, the two are relatively far apart compared to the second segment. All right, then what's going on here in the transition? Now, there's going to be losses because it's an expansion, but it would also be acceptable if you sketched it like this. Let's see here. So we've got a big gap, and it's going, we're losing energy. All right. Now you've got fast V and slow V. And what happens, you know, as per Bernoulli's equation, how does pressure change when you go from fast velocity to the slow velocity? Pressure is increasing, right. So we could say low P and high P. So it might be that the pressure change is actually greater than the loss that you're seeing. And that's what happened in the lab yesterday. Do you remember yesterday in the lab at that expansion, the expansion fitting, the pressure actually increased rather than decreased. And so you could have that we're simultaneously seeing there is the EGL line is going lower, but the HGL line is getting higher. So that would be an acceptable interpretation as well. How much, whether the pressure increases or decreases depends on the relative difference in the velocity between the two. Whether the velocity change is larger than the energy loss. All right, so the other key feature is that the HGL needs to terminate at the water surface, and the EGL is above the water surface to represent that you're losing the velocity head as the water goes into the tank. Okay, are there questions about this one? Okay, let me give you a few more minutes to think through the one on the back, and then I am going to give you that extra minute that I took from you before. Maybe even some bonus, I don't know. Okay, so in this one, it's a little bit unclear because we've got like kind of a side elevated view of the tank, and so you have to make an assumption of where the water level is at. My sketch is assuming that the water level is up to the very top of the tank, but if you assume something different and drew like the water level onto the tank to make it clear, then that'd be all right as well. So what we have is a small pipe and a large pipe. So first of all, looking at the diameters, that means that you're going to have steeper EGL and HGL on the left compared to on the right. That slope is going to be shallower. Likewise, the gap distance between the HGL and the EGL is larger on the first pipe section than on the second. But the really important part is to illustrate that in a pump, you just have a straight vertical line that represents an immediate increase in energy in the form of pressure. That's how the pump is adding the energy. So this is an iterative thing where if you don't draw this, if you don't have this going high enough, then you're not going to be able to get the line to end at the water surface where it needs to be. So sometimes you have to like start at the end and work backwards when you're doing these sketches. You know, like work backwards and start at the beginning, work forward, and then that kind of tells you how long to make that vertical line. Yeah. Mm-hmm.
Did you intentionally put it at the bottom of the pump?
Nope. It didn't have to be below the pump. I could have made it so it was above, and that would still be accurate, as long as this was steeper, the first section was steeper than the second one. But no, it didn't have to be. And also, it was accidental that these are diverging a little bit. That's just kind of some sloppiness on my part. Okay, so that is all for today. Just keep in mind that your next assignment is due on Thursday, a week from today. So please let me know if you've got any questions on that. We'll work through some related examples on Tuesday.